Okay, we are off to chapter 8 here, which is gases. So obviously in this chapter, we're going to talk about gases, gas laws. We'll also talk a little bit about gas stoichiometry as well. So obviously gases are the state of matter where, everybody has pretty much broken apart from one another. They're flying around within a container. And as they are flying around, there are going to have collisions that occur with the container, for example. And the amount of sort of collisions that we have with the container and that occur within a container that has gases in it results in really the pressure that we sort of associate with gases. So let's get started with that. First talk a little bit about substances that basically exist as gases under normal conditions. When we talk about sort of normal conditions, it basically means that we do have a pressure of about 1 atmosphere, and that's what the ATM stands for here. ATM is a very common unit of pressure, which is an atmosphere, and sort of considered like kind of normal roomish type temperatures, 25 degrees Celsius. And under these sort of normal conditions, what we have going on in terms of ionic compounds is they typically will not basically be gases under these conditions. Ionic compounds, as we've talked about, are basically held together. The two ions, positive and negative guy, are held together by very strong electrostatic attractions that kind of opposites attract. And that's a very, very strong attraction. So under sort of normal conditions, you will not get really an ionic compound to go into the gas phase. That's why when we have something like sodium chloride, it will just basically remain a solid. It won't really go into the gas phase very easily. And we see that, when you evaporate off, say, some water in a sodium chloride solution, when you evaporate off the water and you're even left with the solid, you can pretty much heat the heck out of that thing and it will never really go into the gas phase. It will start to melt before it would actually get into the gas phase and stuff like that, because those very, very strong electrostatic attractions. And that's very different than what we see with molecular compounds, which obviously the major difference between ionic compounds and molecular compounds, as we talked about through bonding, is obviously they are sharing electrons here, right? And when we have guys that are sharing electrons, what they end up having in terms of their interactions with other molecules are what are referred to as basically intermolecular forces. So, if you had something like these two guys together, molecule here, and these were both covalent. So say something like water is an actual example here. Water is a polar molecule where the oxygen is more negative, hydrogen is more positive. And these guys are attracted to each other through opposites attract. This is what is referred to as an intermolecular force. And that's what's actually known as hydrogen bonding specifically. And that bond between the two molecules, or two water molecules in that example, is not as strong as something like electrostatic attraction, which is more of an intramolecular force. So what happens when we heat something, for example, like water, it's pretty simple. It can break this bond between the two water molecules, and that allows each of these water molecules basically to go into the gas phase pretty easily. There are certain covalent guys that are basically just gases under normal conditions. So things like carbon monoxide, carbon dioxide, that's hydrogen chloride gas, that's ammonia, and that's methane gas right there. But a vast majority of molecular compounds are liquids and solids at room temperature, but that is the major difference between a molecular compound and an ionic compound. It is much, much easier to convert a molecular compound sort of into the gas phase than you could an ionic compound. And again, it's really because they're held together by these intermolecular forces, which are relatively strong, but not as strong as what you find in ionic compounds. Because pretty much in ionic compounds, everybody's just piled in there together. The positives and the negative guys all kind of structured together in one thing, as opposed to this kind of separation of the different molecules that we get in a covalent molecule. So general rule is, the stronger the attractive force is between one molecule and another, the less likely that it will exist in gas phase. And also, as we'll talk about in a later chapter, the stronger that force, it affects things like boiling points, where the thing will kind of go and start to boil, and also things like melting points as well. Now, under normal condition, these are some of the things that we should be familiar with, right? Are kind of elements that are diatomic elements: hydrogen, nitrogen, oxygen, fluorine, chlorine. These are all gases under normal conditions. They come as those diatomic molecules. Ozone, which is O3, is also a gas. And then obviously our group 8 on the periodic table there, they are all gases. They are referred to as monoatomic. They come as ones, basically, again, as how they normally come. So if we look at the periodic table there, you kind of see, you know, kind of our hydrogen over here, and then kind of starting with nitrogen, oxygen, fluorine, and chlorine. And then again, our group 8 are going to be our gases under normal conditions. Again, everybody else most likely going to be solids or liquids. They're there. Let's talk a little bit about some characteristics of gases. Gases assume basically the volume and shape of the container they're in, and they fill it uniformly. So as we can see here, sort of a gas vapor happening here. When it's in a container, it's basically filling it uniformly, and that's because we assume that it is moving around, so it's constantly bouncing around. And one of the things that we will sort of see in this chapter, and is sort of what happens with gases, is we oftentimes refer to the actual volume of the container itself rather than the volume of the gas that's in there, as the gas is moving around and filling that container sort of uniformly. Gases are the most compressible. Obviously, as you compress a gas down, it gives everybody a lot less room to move around and fly around. What that leads to is a lot more collisions, and obviously a lot more collisions typically will lead to a lot more pressure associated with it. Gases will mix evenly when they are completely confined in the same container. So if you have multiple gases, just by the process of them being in the same container, they are all basically flying around in the same area. So gases are really said to be soluble in one another because, frankly, they're just flying around in the same container, moving through each other, and obviously are, in that sense, mixing really well with one another. Gases typically have lower densities than liquids and solids. So when we talk about density with solids and liquids, the units we usually see are grams per milliliter or grams per cubic centimeter. When we deal with the density of gases, we actually end up usually doing grams per liter. So that's very commonly sort of the units that we associate with the density of a gas, which we'll do some calculations later on to calculate something like the density. But usually it's grams per liter rather than grams per milliliter because of the much lower densities that we see. So obviously one really important aspect of gases is pressure. Pressure is force over area. And there's several units of pressure that we commonly kind of come across. One's a Pascal. Also a kilopascal is sometimes used a lot with pressure. That does equal 1 Newton over meter squared. But really, this 3-pack of units are sort of the most common units that we do see the most, and that is an atmosphere. That's an mmHg, which is millimeters of mercury, and that's a torr, which obviously stands for torr, which is named after the guy over here that invented the barometer. That is a barometer, and that is one way that we sort of measure pressure. Old barometers like this one used to be made out of mercury. And basically it was like a kind of glass tube in a pool of mercury, and then as atmospheric pressure sort of exerted down on the pool of mercury, the mercury would rise or so in the column. And that is really how we get this unit here, because on most barometers there is frankly a ruler where you can measure in centimeters, usually inches, or millimeters of mercury. So that is where the millimeters of mercury comes from, the reading that you would take off of a barometer, kind of from the ruler. Most of them were like centimeters and inches, but we usually do something like millimeters of mercury. So an atmosphere is also equal to 101,000 pascals, or 101 kilopascals. There's other units, obviously, of pressure, PSI, which is pounds per square inch. Bar is another common sort of unit of pressure. A bar is basically almost the same as an atmosphere, is 1.01. So the conversion is very, very close to one another. So 1 atmosphere does equal 760 millimeters of mercury and 760 torr. First off, a millimeter of mercury is basically equal to a torr, so it's a 1-to-1 relationship between those two. So if you have to do a conversion, you basically just change the units. It's basically the exact same number. That 760 number is an important number because it is how we go from atmospheres and back and forth there to millimeters of mercury or torr. So if you have atmospheres and you need millimeters of mercury or torr, you're going to multiply by 760. And that would give you, again, millimeters of mercury are basically torr. And if you have millimeters of mercury or torr, you're going to divide by the 760. And that is going to give you atmospheres. So that 760 is used a lot. There are certain formulas where you do need, obviously, the pressure to be in atmospheres for sure. So we use that a lot. And then obviously, like most sort of formulas that we're going to see, you know, you gotta make sure that the units are the same. So again, converting between those guys is very, very common. Questions on that there? So as we can see, sea level or pressure is 1 atmosphere. As we kind of go up in terms of distance there from the Earth there and sea level, we see that the pressure does start to come down, which is why they pressurize planes and so forth, right, when we're flying. So there are a couple of tools that are sometimes used to measure gas pressure. Manometers are used to measure gas pressure, and there's sort of two sort of ways these are used. One where we do have it sort of sealed up there on the top, and that is in a vacuum type situation. And in this case, if we wanted to basically figure out the pressure of this gas obviously is moving around in here. It's got really nowhere to go, so it starts pushing the mercury. So we can measure the height of the mercury in the column, and that will give us the pressure of the gas in a vacuum situation would equal the height there of our column. Now, in a sort of a open situation, like this guy here, that's obviously open to the environment. So as this gas pushes this mercury, there's also atmospheric pressure kind of pushing back down on it as well. So you do have to take that into account. And that's where we see here that the pressure of the gas is the height plus the atmospheric pressure as well. So you have to take that sort of into account as well when you're using it sort of open to the environment. So we're going to talk about several gas laws here. And when we talk about gas laws, there's kind of 3 variables that we oftentimes deal with, which is pressure, volume, and temperature. And some cases, one of these are held constant, the other ones are changing. Some cases, none of them are held constant. Everybody's changing. So we could use a tool like we were just looking at there to see what's going on. The first thing we're going to look at is the relationship between pressure and volume. And we're going to hold temperature constant. And what we see here is at 100 milliliters, we have this much pressure basically. And at 50 milliliters, we start to see the pressure increase. And at 33 milliliters, we basically see a lot more pressure happening. So the general sort of form that we see in terms of relationship here, which is known as Boyles Law, we'll see on the next slide, is basically as the pressure goes up, the volume goes down, and vice versa, sort of inverse relationship. Pressure goes down as the volume goes up. And this makes sense if we think about gases which are flying around. Obviously, as you squeeze down the volume, that gives everybody a lot less room to fly around in. And that definitely should increase the number of collisions that we see. And because we're increasing the number of collisions, that obviously should increase the pressure. If we do the opposite and basically increase the volume, gives everybody a lot more room to fly around in. Going to take longer for collisions to occur. When it takes longer for collisions to occur, we're going to see less pressure associated with that. And again, that's sort of what we see if we kind of headed in the opposite direction here, increasing the volume, we decrease the pressure. So as I mentioned, that is basically Boyle's law. And that is it right here, which is P1 V1 is equal to P2 V2. And once again, if we look at a graph of Boyle's law here, pressure versus volume, that's exactly what we see. Again, at a smaller volume, a much higher pressure at a more larger volume, a lower pressure sort of occurring at this point. There is sort of a linear relationship that we get, which is again, a sort of that inverse relationship. As the pressure goes up, volume goes down, and again, vice versa, as we just talked about there. Now, when we look at this, and in a Boyle's law situation, if you keep the temperature constant, you could take any pressure and volume measurement that you make, and it will always equal what is sometimes referred to as the proportionality constant. And proportionality constant, which is what I scribbled there, I think, is basically a constant number. So in a Boyle's law experiment, and we used to do this occasionally, you could actually continue to take pressure volume relationships, and as you multiply them, they always equal the same number for sort of the same gas. And because of that, we could set them equal to each other and get Boyle's law, which is our P1 V1 is equal to P2 V2. And again, this is at constant temperature. In terms of pressure, it could be any unit you like, as long as the units are on both sides the same. So obviously, so that they cancel out. And same thing with the volume here. The volume can be any unit you like, again, as long as they're the same on both sides. So everything obviously cancels out correctly. So let's take a look at one here. A sample chlorine gas occupies 946 milliliters at 726 millimeters of mercury. What is the pressure when the volume is reduced to 154? So take a moment and see what you come up with. Let's take a look here. And a good thing to do in sort of gas law sort of problems is kind of pull out the information. So obviously here we have a volume that's 946. We have a pressure, which is 726 millimeters of mercury. We're looking for another pressure here, and we have a volume that is 154 milliliters. So again, although we only have learned so far one gas law, obviously we have two pressures and volumes. So it would be Boyle's law here. It doesn't really matter, but most people just kind of name the first stuff ones and the second ones twos here. In terms of volume, they're both in the same units, so we're good. So we don't have to do any conversions. So we could rearrange and solve for P2. P2 would equal P1 V1 divided by V2, bringing this to the other side. And putting in our values here would give us 726 millimeters of mercury, 946 milliliters, and a 154 milliliters. Milliliters here will cancel, and we will end up with about 4460. And that would be millimeters of mercury in this case. First off, any questions on the calculation? Again, a good thing to understand is the relationship that we talked about here, especially with Boyle's law, which is pressure goes up, volume goes down, pressure goes down, volume goes up. In this particular case, the volume went down, which means we should see the pressure go up. So it started at 726, ended at 4460. So it did go up, and that makes sense. And again, it's a good way to sort of check your calculations because it's very, very common place in gas law problems that people sort of invert numbers a lot of times and put, V1 for V2 and things like that. So again, if you saw in this particular case that the pressure went down, then obviously mathematically something probably went wrong as well. Any questions on that there? All right, so try this one. Inflated balloon has a volume of 0.55 liters at sea level, and it rises to 6.5 kilometers where the pressure is 0.4. What is the final volume of the balloon here? Okay, let's take a look here. So once again, pulling out the information, we got a volume that's 0.55 liters. We got 1 atmosphere, which is a pressure. We got 6.5 kilometers, which is useless information. And we got a pressure of 0.4 atmospheres. And we are definitely looking for a volume. So again, you can hopefully kind of see Boyle's law there. Once again, here we are going to be solving for V2, which would be P1 V1 divided by P2. Once again, dividing it to the other side. By the way, just quickly in terms of rearranging these sort of gas laws, you can think of the equal sign. You can think of these like as fractions. So if you move something to the opposite side of the equal sign, it ends up in the opposite location. So that guy was there, so it ends up on the bottom. It's kind of a quick way to rearrange things. Gives you 1 atmosphere. We have 0.55 liters and 0.4 atmospheres. Once again, here the atmosphere is going to cancel. In this case, we will be left with liters, which is a volume. And this will get us 1 times 0.5 divided by 0.4. That is not right. 1 times 0.55 divided by 0.4. There we go. Gets us a volume of 1.3, about 1.4 liters in this case. Once again, we could check and see if it sort of makes sense. So in the case, in terms of the pressure here, we're seeing the pressure go down, which means the volume should go up, and it started at 0.55 and ends at 1.4. So again, it does make sense based on Boyle's law. Any questions on that there? Yep. The the thing that we're going to talk about is sort of the relationship between volume and temperature, and also pressure and temperature. What we're looking at here is actually temperature and volume, and what we see here is that low temperature. We have a low amount of gas, or a low volume of gas, smaller volume of gas. At the higher temperature, we end up with a larger sort of volume of gas. And under V and T here, this is what was referred to as Charles' law. And it is V1 over T1 is equal to V2 over T2. And this would be at constant pressure. This is sometimes referred to as Guy-Lussac's law. And this P1 over T1 is equal to P2 over T2. And this is at constant volume. And what we're looking at here in these pictures is actually sort of Charles' law relationship. So when we have a situation where the volume is able to move, that is the real reason why it's able to really keep constant pressure. So if we increase the temperature and the volume does not move, so that would be like this case over here. If we increase the temperature and the volume is pretty much rigid, it does not move, what we would expect to happen is the gas molecules will be flying around a lot faster. As they're flying around a lot faster, there should be a lot more collisions that should be occurring, and we should see an increase in the pressure. And that's exactly what we see here in this situation. If we increase the temperature, we will see the pressure go up because the volume is locked into place. Vice versa to that is if we decrease the temperature in the situation on the right there, Guy-Lussac's law, the gas molecules are going to fly around a lot slower, which means it's going to take longer for collisions to occur. And what we will see is actually the pressure start to come down. So we see in this situation, temperature decreases, so does the pressure. So this is a situation where the volume is locked into place. It cannot adjust. So that is exactly what we would expect to happen. And sort of Charles' law, what happens is the volume is not locked into place, so the volume can adjust, and that's exactly how it's able to keep the pressure constant. So when we increase the temperature, just like we did over here, we would expect the pressure to increase because the volume is locked into place. But in Charles' law, what happens is the volume itself actually increases with it. And because the volume increases with it, even though the gas molecules are flying around as faster, there's a lot more room for them to fly around. And what it does is it keeps the number of collisions relatively constant, and that keeps the pressure constant in that situation. So in Charles' law, as the temperature increases, so does the volume. And that, again, is what keeps the pressure from going crazy and remains constant. And vice versa, what ends up happening if we lower the temperature in a Charles' law situation, the gas molecules will again be flying around a lot slower, and that's going to decrease the number of collisions. So to fix that, what happens is the volume basically squishes down. So it has a lot less room for everybody to fly around in. So even though they're moving slower, the volume sort of closes in on them. And that again keeps the number of collisions relatively constant. And that's what keeps the pressure constant. So in a Charles law situation, which is on the left there, the V1 over T1 is equal to V2 over T2. We have the volume really adjusting to allow the pressure to remain constant and really to allow the number of collisions to remain constant, whether you increase or decrease the temperature. Sort of the Guy-Lusick situation on the right there, where the volume cannot do that because it's locked into place. We get the actual changes that occur in the pressure as the temperature increases. We have more collisions and we start to see a rise in pressure. And as the temperature decreases, we get less collisions and the pressure starts to come down. Any questions on that there? So this is Charles' law. And again, if you take an actual graph of any gas you like, and you graph basically the volume versus the temperature in Celsius, and you extend the line for that graph all the way back to the temperature axis, they will all hit the exact same number, which is minus 273.15 degrees Celsius. That number is important. That is the number that we use to convert to Kelvin. And Lord Kelvin there basically realized that, because if I wanted to convert this to Kelvin, I would add 273.15, which gives me 0 Kelvin, which is absolute zero. And that means that for the most part, every single gas law you come across, the temperature does need to be in Kelvin. So you do have to convert every gas law that has temperature into Kelvin. And again, that is Celsius plus a 273, obviously, to do that. That means when we look at our two gas laws from the previous page there, each of these do need to be in Kelvin for sure. And like I said before, if you're doing a gas law and you have something to do with temperature, you do need to make sure it's in Kelvin. Otherwise, you will get the wrong answer. And that includes problems where people sometimes make a mistake because they give you the temperature in Celsius. They ask you to give the answer in Celsius. So people think, okay, they want Celsius. They gave it to me in Celsius. I could leave it in Celsius. You will get the wrong answer. So you have to convert it from Celsius to Kelvin, put it into the gas law. And then once you solve the gas law, convert it from Kelvin to Celsius again. So you got to have it in Kelvin when you do that. Again, even in a situation where they give it to you in Celsius and they ask you to convert it to Celsius, it's got to go into Kelvin to that gas law. Any questions on that there? All right, so let's try one here. Sample carbon monoxide occupies 3.2 liters at 125 degrees Celsius. At what temperature, we'll go with Celsius, would the volume be 1.54 liters? We'll go with degrees Celsius. Okay, let's take a look. So we can pull out our information here. We got our volume is 3.2 liters. Our temperature is 125 degrees Celsius. And we are looking for a temperature, and our volume there goes to 1.54 liters. At this point, we got a few gas laws to choose from. P1 V1 is equal to P2 V2. V1 T1 is V2 T2, and P1 T1 is P2 and T2. In this case, obviously, there's no pressure, so that clearly eliminates that. That puts us to Charles' law, which hopefully you can kind of see from just pulling out the information. We'll call those ones. We'll call these guys twos. In terms of conversions, we do need to convert this guy into Kelvin, even though, once again, we are looking for Celsius at the end, but it does need to go into Kelvin to go into our gas law. So we're going to add 273 to it. It's going to give us 398 Kelvin. In this case, we have V1 T1 is equal to V2 T2. Once again, quick way to sort of rearrange, if you like, is just to move everything to opposite sides. In this case, we are looking for T2, which means it needs to go up there. And all those other guys need to go in the opposite location. So this guy has got to go there, and this guy has got to come across there. So that's going to give us T2 is equal to V2 T1 V1 when you rearrange it, basically multiplying T2 to both sides. And then multiplying T1 to both sides. And finally, dividing our V1 to both sides at the end there, gets us over to there. At this point, we're going to put in our numbers, hopefully correctly. So we're going to go with V2, which is 1.54 liters. We want T1, which is 398 Kelvin, and V1, which is 3.2 liters. Those guys are going to cancel. And that is going to get us something 1.54 times 398 divided by 3.2 gives us about 192 Kelvin. And again, in this case, if we did want it in Celsius, we would subtract 273 from that. And that will get us approximately like 81.4 degrees Celsius. Just 81 degrees since I rounded there. Any questions? It's actually negative 81.0 degrees Celsius. We could check to make sure this makes sense. Here we do see that our volume goes down, so we should see our temperature goes down in this case. And obviously it started at 125, ended at negative 81 degrees Celsius. So definitely it did go down. Even the Kelvin temperature, if we just look at the Kelvin temperature, went down from 398 to 192 in this case. Any questions on that there? All right, I'll try another one here. An experiment, 452 milliliters of a gas in a light bulb heated from 22 to 187. What is the final volume here? We got a volume that is 452. It's heated from 22 degrees Celsius to 187, and we are looking for a final volume. So again, hopefully you can see V1 over T1 is equal to V2 over T2 here, and we'll call those guys these. We're going to add a little 273 to both of these temperatures to get them into Kelvin. And that would get us 22, 273, 295 Kelvin. And 187 plus 273, 460 Kelvin. And obviously, we're going to leave our volume here in milliliters. So we will end up with milliliters at the end. In this case, we're going to move our T2 to the other side. So it goes opposite location. So that gives us V1, T2. T1 is equal to V2. Putting in our numbers correctly here would get us 452 milliliters, our T2, which would be 460 up on top. And our the Kelvins here will cancel, and we'll end up with 705 milliliters in this case. So once again, if we look at our temperature goes up in this Charles Law situation. We should then see our volume go up as well. And that's what keeps it at constant pressure. And again, that's what we do see 452 to 705. So again, we see the increase in the volume as we should expect here. Any questions on any part of that there? All right, one last one of these here. Argon gas, a certain light bulb containing argon at 1.2 atmospheres at 18 degrees is heated to 85 degrees. What will be the final? Okay, so we got a pressure here of 1.2 atmospheres and a temperature of 18 degrees Celsius. We have another temperature of 85 degrees Celsius, and we are looking for a pressure. So once again, that is our P1 T1 is equal to P2 T2. Once again, like every other gas law, we got to do our temperature into Kelvin here. And if we do that for each of them there, 18 plus a 273, it's like a 291 Kelvin, a 85 plus a 273 gets us a 358 Kelvin. At this point, we're good. We're going to solve for P2. So what should be that guy? We're going to, once again, kind of send this to the opposite location over there. So that will give us P1 T2. T1 is equal to P2. Once again, we want to put our right numbers in the correct spots. So 1.2 atmospheres times our T2, which is 358, divided by our 291 Kelvin. And that would equal our P2, which looks like by 291. Looks like here 1.48 atmospheres, if I punch that in right. Good. And again, in this case, if we look at it, what we're seeing here is our temperature is increasing. So we would expect in this case, our pressure to also increase as well. And it is obviously going up to 1.48 in this particular case. Any questions on Charles' law, Guy-Lussac's law here? Okay. All right, so the next law we're going to talk about is our good friend Avogadro. You know, he had a number, but he also won a gas law. When we think about Avogadro's number, we think about moles. So it is not surprising that Avogadro's law here involves moles, and it's right here. And it is basically V1 over N1 is equal to V2 over N2. And this is that constant, as it says here, temperature and pressure occurring at this case. N is the moles, so N is the number of moles. And so you could use this, obviously, relationship like we normally would for the gas law. You could plug in, obviously, some volume, some moles, and figure out moles, or if you have moles and volume, figure out volume. But there is another sort of application of Avogadro's law here, and it is sort of used in sort of stoichiometry problems that involves gases that are under constant temperature and pressure. So when we do sort of stoichiometry problems from an equation like this, we oftentimes will use the mole to mole relationship. And again, that's just the coefficients, right? 3 moles of H2, 1 mole of N2 gives us 2 moles of NH3. In a constant temperature and pressure situation, if you're dealing with all gases, like in this particular problem, and you're maybe interested in a volume, which is a common thing that you are usually asked to sort of find with gases is, you know, how much volume or something like that. You could actually do sort of a volume to volume relationship using the equation, just like you would do a sort of mole to mole relationship. So we could use the coefficients, for example, and say something like 3 liters of H2 react with 1 liter of N2 to give us 2 liters of NH3. So those numbers, again, come from the coefficients, just like the mole to mole relationship. And it's a nice way sometimes when you're doing gas stoichiometry under sort of constant temperature and pressure conditions, that you don't have to use a gas law to sort of solve the problem. You could kind of just do like a little stoichiometry situation. So if we look at this and we have ammonia burns in oxygen to form nitric oxide, how many volumes of NO are obtained from one volume of ammonia at the same temperature and pressure. So this is the key here. We have constant temperature and pressure in this situation, and we're interested in how much NO is here. So from the equation, we could really do a mole to mole relationship. We could see that, there are 4 moles of NH3 gives us 4 moles of NO. So that's sort of our mole to mole relationship. But in order to use that, we would need some more information in this case, which we don't have to kind of help us do that. So the sort of nice relationship we could have is that there would be 4 liters of NH3 is equal to 4 liters of NO. Now, this sort of relationship, which comes from Avogadro's law, we could use to help us answer this question, because they basically asked us if we started with 1 volume or like 1 liter of NH3. We then could do a stoichiometry calculation with liters and go from the equation, there's 4 liters of NH3 or 4 liters of NO. The liters of NH3 would cancel out, and that would give us 1 liter of NO would be produced in this case. So we could do sort of a stoichiometry problem using liters or volumes in a situation like this where we have constant temperature and pressure. What this will allow you to do is sort of bypass using a gas law, like we'll talk about a little bit later on here, something like the ideal gas law or something like that, without having to sort of incorporate that into the stoichiometry problem. So it's a nice little workaround if you're looking for volumes and you have constant temperature and pressure. Just do like a volume to volume relationship, and that is will work out okay because of Avogadro's law. In addition, obviously, like I mentioned before, you could just plug and chug into Avogadro's law and sort of solve some problems that way as well. Any questions on that there? All right, so just to review some of the stuff that we've been talking about, Boyle's law, we saw again, as the pressure goes up, the volume goes down. Again, it squishes everybody down there, as you can see, and that's going to increase our pressure. And as we sort of increase the volume, the pressure starts to drop. It gives everybody a lot more room to move around in. We saw with Charles' law and Guy-Lussac's law, again, heating and cooling gases, lower temperatures. We will see that the volume will decrease to keep that constant pressure. And again, it will increase to allow the pressure to remain constant and help out with the number of collisions when we can adjust the volume. Obviously, when we cannot adjust the volume and it's constant like we have here, we will see the increases that we expect to happen. Lower the temperature, we will see the drop in pressure. If we increase the temperature, we will see a higher pressure, again, because the volume here is locked into place. It's not adjusting like it is up here. So along with that, in Avogadro's law, which deals with sort of moles and volumes, which are sort of related to each other, as one sort of increases, the other one increases as well. Putting all those guys together, we get the granddaddy of them all there, which is the ideal gas law. And the ideal gas law is PV is equal to nRT. And PV equals nRT is a little bit different than some of the gas laws that we've seen before. The first major difference is it is sort of a one and done situation. There's like no before and after. So there's no 2 pressures, no 2 volumes, no 2 temperatures, just one of everything. The other really important thing about the ideal gas law is, out of all the gas laws, it is the most restrictive in terms of units. So when you use PV equals nRT, the pressure has to be in units of atmospheres. The volume has to be in units of liters and has to be in units of moles. And temperature has to be in units of Kelvin. So it is a must if you're using PV equals nRT that everybody are in these units. The real reason for that is because of R. R is the gas constant, and R has a value of 0.08206. And it has these units, liters times atmosphere, divided by Kelvin times mole. So the good news is usually R is given to you somewhere. So, if you're can't remember what everybody needs to be in, that tells you every unit that everybody needs to be in that gas law as well. If you want to use a rounded number, I use the other one because it was beat in my head and I can't get it out. But some people will round that to 0.0821, which is perfectly fine as well. And that is a value as well that you always have given to you, or I guess you always have available to you, but not always given to you in problems. So a lot of problems, they don't even mention anything about the gas constant. Just assume that you understand that you have that sort of available to you. So if you go through a problem, you got a pressure, you got some volume, you got maybe some moles, and you're looking for temperature, but you're kind of missing R. That again is a value that you should always have. So let's talk about a couple of other important relationships there with the ideal gas law. One important relationship is what is known as STP. STP stands for standard temperature and pressure. So when somebody says, hey, this is at STP, they're actually giving you a temperature and a pressure. The temperature is 273 Kelvin. The pressure is 1 atmosphere. So those are the actual values that you use when somebody says we are at STP. Now, one really nice conversion that you could use when you are at STP and only at STP, 1 mole of any gas will equal 22.414 liters. So this conversion that you could use when you're at STP is a nice one because it allows you not to have to use the ideal gas law. So you could kind of use this without using the ideal gas law. But it should be noted that you do need to be at STP in order to use that. So if the temperature is not 273 and the pressure is not 1 atmosphere, you should never use that. You should use the ideal gas law to solve your problem. The good news is you can use the ideal gas law in any situation, STP conditions, non-STP conditions. So if you use the ideal gas law in STP conditions, you just put in for your temperature 273 and for your pressure 1 atmosphere. So always use the ideal gas law in any situation. If it happens to be STP, you could not use the ideal gas law, can use that conversion. But again, if it's not STP, don't use that conversion factor. That, by the way, is how we get the value of the gas constant. We basically put in all that information into our ideal gas law and solve for R, and that gives us the gas constant of 0.08206 basically as our value there. All right, let's try one here. Calculate the pressure exerted by 1.82 moles of SF6 gas in a steel vessel with a volume of 5.43 liters. And let's take a look. So if we just pull out the information, we are looking for a pressure. We have moles of 1.82. We have a volume of 5.43 liters, and we have a temperature of 69.5 degrees Celsius. So you can hopefully see that obviously the only gas law that would make sense here would be our PV equals nRT, since we pretty much don't have 2 pressures, volumes, or anything like that. In terms of units, we're good here. We're good here in terms of liters, but once again, we need to convert our temperature, which would be 69.5 plus a 273, 342.5 Kelvin. Remember that we always have R given to us or available to us, which would be our 0.08206. So in this particular case, we are solving for pressure. So we're going to divide the volume to the other side. That will give us P is equal to nRT divided by V. Putting in our numbers here, 1.82 moles or 0.08206 liters atmosphere Kelvin mole, and our 342.5 Kelvin, all divided by our volume of 5.43 liters. The moles cancel, the Kelvin cancel, the liters cancel. That leaves us just atmospheres left over, which is good since that is what we are looking for. Pressure 1.82 times 0.08206 times of 342.5 equals divided by 543 gives us a 9.42 atmospheres here as our pressure. Any questions on that calculation there? Variations of this obviously is a lot of times you may be given, grams. You have to use the molar mass to get the moles. So again, it's a common one as well, in addition to the temperature. And again, a lot of times gases are collected, are measured in milliliters. So converting milliliters to liters here is another very common thing that you have to do with the ideal gas law. Any questions on that there? All right, so why don't you give this one a go? What is the volume in liters of 49.8 grams of HCl at STP? Hydrogen 1.008 and chlorine 3540. Okay, let's take a look here. So we're looking for a volume here. We have 49.8 grams of HCl, which we could get into moles. And we have STP, which means the temperature is 273 Kelvin and the pressure is 1 atmosphere. Put the 1 there. And that means we also obviously have R. So we can use the ideal gas law here. That is PV equals nRT. Once again, we solve for V. V would be nRT divided by P. In this case, the only conversion we need to do is convert our grams into moles. So we basically just need to add that together, which would be 3646. And that would get us 49.8 grams of HCl divided by our molar mass here. That's going to give us 49.8 divided by 3646. Looks like 1.37 moles. So our volume would be 1.37 moles times our R. And our temperature, which would be 273, all divided by our pressure, which would be 1 atmosphere. Atmospheres cancel, Kelvin cancel, moles cancel, leaves us liters when it's all said and done. We end up with about 30.7 liters here of our guy. Any questions on that there? Now, could we have solved this another way? The answer is yes, we could have. Because we are at STP, that is the time where we can use that relationship that 1 mole is 22.414 liters, which means we could have just took our moles and multiplied it by 22.414 liters and would give you 30.7 liters. So again, it's a good demonstration that in this case, if you remembered the sort of conversion there, because it was at STP, you could have used it, but also a good reminder that you don't need to use it. You could also use, obviously, the ideal gas law and just put the values in there. Any questions on that there? So far we talked about sort of changes in one variable or a couple of one variable, two variables, keeping one constant. But there also is another gas law where we do look at sort of changes in all 3 of those variables, so pressure, volume, and temperature. If we take the ideal gas law and solve it for R, which is the same number, we could set those guys equal to each other. And in most cases, if you don't open the top there, the gas moles will not leave. So those guys remain constant. So that gets us down to what is sometimes referred to as the combined gas law. And that is P1 V1 over T2 is equal to P2 V2 over T2. And this is sometimes referred to as the combined gas law. Good news here is pressure could really be any unit you want on either side, as long as they're the same. Same thing with volume, but like every other gas law, once again here, our temperature does need to be in Kelvin. So do need to make sure our temperature, once again, is in Kelvin. Again, rearranging of this one does give people a little bit of difficulty sometimes. So again, if that's an issue, make sure you take some time to figure out how to properly rearrange these things here. So why don't we give it a try and see how we do. Consider a sample of oxygen gas at 27 degrees with a 9.55 liters and a pressure of 2.97. We change the pressure to 8.25 and we heat it to 120. Okay, let us pull out the information here. So it looks like we got a temperature 27 degrees Celsius. We got a volume 9.55 liters. We got a pressure of 2.97 atmospheres. Got another pressure of 8.25 atmospheres and a temperature of 125 degrees Celsius. And we are looking for a volume. So this definitely is our P1 V1 over T1, our combined gas law here, P2 V2 over T2. In terms of pressures, they're both in the same unit, so that's good. Once again, not surprisingly here, our temperatures do need to be converted. So we'll add a 273 to it. That makes this guy 300 Kelvin. And a 125 plus a 273 makes this guy a 398 Kelvin. Calling all these guys on the left there are ones, guys on the right there are twos. We're going to solve for V2 here. So basically, we're just going to move everybody to the other side in opposite locations. So this guy here will go up. This guy here will go down, basically. And that will then get us P1, V1, T2 is T1, P2 is equal to our V2. Put it in our numbers here in the right spots. We're looking for, looks like P1 up on top. So that's a 297. A V1 is a 9.55 liters and a T2 in this case, which is 398 Kelvin, all divided by our T1, which is 300 Kelvin, and our P2, which is 8.25 atmospheres. Atmospheres here cancel, Kelvin cancel, leaves us with liters, which is good since we are looking for a volume here. That's going to give us 2.97 times 9.55 times a 398 divided by a 300, and lastly divided by an 825. Looks like a 4.56 liters in this particular case. Any questions on that there? Okay, any questions on any of the gas laws that we talked about here? You obviously do need to know them, and that's a good spot to stop for sure. Yep. All right, we'll lay it up there for today. A reminder that we are quizzing on